So I'll start with a polar representation of a vector. So in this case, we pick some vector in Rk and we represent it by a pair r and theta, where r is the norm of the vector and theta gives some sign-valued function on the circle, or the sphere, the k-1 sphere, given by the sign of the inner product of some vector on the circle with the vector, vector A. So here, for example, if you're on this part of the circle, you would have a positive sign, and then here the orthogonal part would be 0, and pointing away from that vector would be negative. And something related to this is an oriented matroid, which is oriented matroids have a bunch of definitions, and one way of defining them is as a set of sign vectors that satisfy certain axioms. And I don't really want to go into what the definition of the axioms are, although the axioms are symmetry, composition, and vector elimination. But rather than talk about the axioms, I want to talk about where they come from. And one place that they arise is if you have a configuration of vectors and you look at this theta part of the polar representation of a vector for each of the vectors that you have in your vector configuration, and you look at the range of the product of all of these thetas, then you get an oriented matroid. So here I have just one vector, but let's say I add two more. Then I get also some additional sign-valued functions on the circle. So here, for example, I have, if you start on the right here the first elements of the vector would be corresponding to red and yellow and blue. So if I start on the right here, red is in the negative part because this is pointing away from red. And then yellow is positive and blue is positive because it's pointing towards blue. And then as I go along, it stays the same until I get to this point. And here both red and yellow are 0, but blue remains positive. And then red and yellow switch so that red is now positive and yellow is negative, but blue remains positive. And I can keep going around the circle. And as I keep going around the circle, I get each of these signs. And
what is yellow?
So yellow is this vector coming down here, and the sign corresponding to the middle element of each of the vectors corresponds to the yellow one. So this would be red, yellow, blue. And the set of signs that you get define an oriented matroid. So this is one way that they arise. And for example, when one of the axioms is symmetry, which means that if you switch the role of plus and minus, then you also have a vector in your set of vectors, sign vectors. So for example, here is minus plus plus. There's also plus minus minus. But not all oriented matroids can be realized by vector configurations. So there was some question of maybe you could add to these axioms. So we have these three axioms. You could add to that all of the axioms of real numbers, and you could add an additional axiom saying that your sign vectors have to come from real numbers in this way, and that would give you some axiomatic description of oriented matroids, something like oriented matroids, but you only get things that come from vector configurations. But to do that, you would have to change the language to include some variables for real numbers. So if we say that we just don't want to change the language, but we might want to try to add additional axioms in order to get a complete description so that every set of sign vectors that satisfies our axioms also arises from a vector configuration. But we can't do that. So it was proved in 1978 that the missing axiom of matroid theory is lost forever. And other people thought, well, this paper, it had a lot of restrictions on what the language, maybe we can relax that restriction without really going all the way to real numbers. We can have a broader language that still only deals with plus and minus. So more recently, there was a paper where people asked, is the missing axiom of matroid theory lost forever? And a few years later, they proved more recently, yes, it really is. You can't get a complete axiomatic description that's both necessary and sufficient for a set of sign vectors to come from a vector configuration.
That's the actual title of the paper, right?
These are the titles of the papers. So given these circumstances, we want to ask, to what degree do oriented matroids reflect the properties of vector configurations? And one question in that direction is whether vector configurations and oriented matroids have the same global topology. So for this, we want to consider... Yeah?
Before I do get lost, how is this related to the work of Nikolai Neff and Jürgen Richter-Gebert about realizability of matroids?
Yes.
Does this make sense?
Yeah. So this is exactly. So the point that not all oriented matroids can be realized means that you have some oriented matroids that cannot be realized.
Right.
And there's also a hardness question maybe of...
Right. So and how does this, the missing axiom, how does that relate to that work? The question which matroids can be realized.
So as far as I remember, it's like no matter how you make a list of finitely many some logic formulas to add into the matrix theory axioms, you still cannot say it is precisely the realizable matrix.
So you might want to have a set of conditions that tell you whether it's realizable or not. And there's an obvious set of conditions, which is algebraic formulas using real numbers, but you might want to say you don't want to expand the language. And if you don't want to expand the language, you just want to talk about plus and minus and have some language that only involves plus or minuses, then you can't. You can't give a necessary and sufficient conditions to decide realizability without expanding the language to include real variables or something beyond.
What is the point of the 2014 and 2018 work?
So I don't want to go into details that, but they change what do we consider a broader language. So there they consider something more like monadic second order logic rather than just first order logic, something like that.
Okay.
But
thanks.
so if we go to what is the global topology of vector configuration? So by this I mean the topology of the Grassmannian, which can be defined in various ways, but one way is you can look at n vectors that span R to the k and then mod out by the general linear group, and you get some manifold, which is the Grassmannian. And then I want to look at what is the topology of oriented matroids. What does that mean? The global topology. So for this, I look at the Macphersonian, which is the set of rank k oriented matroids. So I didn't go into what the rank of an oriented matroid is, but if you have a set of k vectors in R to the k, then it would give you something of rank k on n elements ordered by specialization, which is also degeneracy. So I'll go into some examples about what these mean, but essentially the point here is this is some poset on oriented matroids. But a poset is not a topological space. So we take the polyhedral chain complex. We look at chains in the poset. And for each chain, we have some simplex, and we get a simplicial complex. And this now gives us some topological space. And then in what sense do they have the same global topology? Well, to ask a more precise question now, we can ask, are the Grassmannian and the chain complex of the Macphersonian homotopy equivalent? So for this, I'll give some example in when k is 2 and n is 3. So if we look at the 2-3 Grassmannian, this consists of vector configurations consisting of 3 vectors in R2 that span the space, so they have rank 2, and then you mod out by the general linear group. And you can also think of this as, consider this, if you put these vectors together in a 3x2 matrix, then you're looking at 3x2 matrices that have full rank. And if you mod out by the general linear group, you preserve the null space of the matrix. So you're looking at subsets of R3, which are the null space of some 3x2 rank 2 matrix. And if you're looking at the null space of some 3 by 2 matrix, those are just lines in R3. And the space of lines in R3 is the projective plane. So the 2-3 Grassmannian is homeomorphic to the projective plane as one side. And then we can look at the Macphersonian. So if we look at rank 2, 3 elements, a 3-element oriented matroid with rank 2, there are 13 possible oriented matroids, and here are all 13 of them. So at the top we have the most degenerate one, the most generic oriented matroid. So in general, not all oriented matroids can be realizable, but in the case of rank 2, 3 elements, all of them can be realizable. So I can represent each oriented matroid by some vector configuration and then order them by degeneracy. So at the top I have the fully generic oriented matroids, each represented by some vector configuration. And then I have a middle level where I have one degeneracy. Either I have 2 pointing in the same direction, or I have 2 vectors pointing in opposite directions. And then at the bottom I have the most degenerate ones. However, there is the requirement that they have to span the space, otherwise the rank would be less than 2. So the most degenerate I can make it is by making one of the vectors go to 0. And then you can see how they're related. For example, if I look at this one here, the yellow and the blue vectors are pointing in the same direction. I could make them more degenerate by having the yellow vector vanish or having the blue vector vanish. But I can't make the red vector vanish. So these are not related because then it wouldn't span the space anymore. And this would be making some things more degenerate, but other things less degenerate. On the other hand, I could go up by having the blue vector move in a little bit or having the yellow vector move in a bit. So this gives some poset. And here I ordered the poset in such a way so that you can see the most degenerate things at the top and the least at the bottom. But I could rearrange how this is ordered like this. So how did I do that? Well, I kind of moved things around a bit. I have these 4 at the top, and these which have these thick outlines, and I have these 3 at the bottom, which are kind of shaded, and then I have these other 6 in the middle. But wait, here you might see there are 9 in the middle. So now I suddenly have a bunch more. So what did I do here? Well, some of them I put 2 times in order to make it easier. So if you look, this is actually the same element as this. And this is actually the same element as this, and this is actually the same element as this. So if you look at the chain complex, for every chain, so here would be an example of a chain. I have this at the top, and then a middle level oriented matroid, and a bottom level oriented matroid. This gives me a simplex, a triangle in my simplicial complex. And if I look at all of these triangles together, I get a subdivision of a disk. But here I have some identifications. If I go around the outside of the disk, then I see at each point around the outside of the disk, there's a corresponding opposite point which becomes identified to the same point. So if I make, now I'm going to make another picture by, I'm just going to keep the most degenerate ones and make the least degenerate ones points and the middle level ones lines. So I get a picture like this. Here I have some triangulation. The 2-3 Macphersonian gives me some triangulation of a disk, but where opposite points on the disk are identified, which is exactly the projective plane. So this is another way to see that I have the projective plane, which is the same as for the Grassmannian. So in the case of rank 2 with 3 elements, they are actually homeomorphic. So what about rank 3? Suppose we go to rank 3 instead. So in rank 3, we have a map that for every element of the Grassmannian, we have a corresponding oriented matroid by taking the signs on the sphere. And then we can say, well, how nice of a map is this? Is this map going to give us a homotopy equivalence? Well, there are some bad things about this map. One is that it's not surjective. So the fact that we have some oriented matroids that are not realized by some vector configurations means that this map is not onto. And another point is, if we fix some oriented matroid and we look at the pre-image of that oriented matroid in the Grassmannian, the preimage can be horrible. It can be disconnected. It can have holes. In fact, for any semi-algebraic set, there is some oriented matroid such that the preimage in the Grassmannian will have the homotopy type of that semi-algebraic set. So the preimages are as terrible as you might think. So in order to deal with this, but it doesn't mean that this isn't true, although it does, that they are not homotopy equivalent, but it puts some shade on that idea. But to do this, I want to introduce another space, which I call the pseudo-linear Grassmannian, and I denote by PSG, which I will show is homotopy equivalent to the Grassmannian. And it has some other nicer properties. One is that the map, every element in this space will have a corresponding oriented matroid, and that map will be surjective, and also the preimages of that map will be contractible. So now I want to define this space PSG for pseudolinear Grassmannians. So to do that, I'll go back to the polar representation. So here I have, for some vector, I have some r, which is the norm, and my map from the circle to signs plus 0 and minus. And to make a pseudosphere is any homeomorphic image of one of these thetas, which is defined by some vector. So for example, if I start with some vector, and I get some division of the sphere into some cap, which is some hemisphere which is positive, and I have a negative hemisphere, and then I have a circle around the middle which is 0, then I can just do some homeomorphism of the sphere. Then what I obtain is a pseudosphere. That's the definition of a pseudosphere. And a pseudosphere arrangement is just a set of pseudospheres where any subset of the pseudospheres, if I look at the 0 set and I look at the restriction of the pseudospheres to the 0 set of some subset, then I get again a pseudosphere arrangement, which means that these pseudospheres have to intersect in some sense like pseudospheres. So understanding this definition maybe takes a while, but you can get some sense by looking at rank 3. So here would be a picture in rank 3. Here I've only drawn one side of the pseudosphere, but since any two pseudocircles should intersect in something like a 0-dimensional sphere, which consists of 2 points, if I pick out any two of these, they should only intersect in 2 points. So for example, this red one and this blue one, they intersect in 1 point in the front, and they would also intersect in 1 point in the back. And if you have some third pseudosphere like this purple one, it should separate the other 2 points where so this purple pseudocircle, the 0 set of this purple pseudocircle should separate the 2 points where the red and the blue intersect. So a theorem of Folkman and Lawrence says that every oriented matroid can be realized by a pseudosphere arrangement. But now I want to go to, rather than looking at these pseudospheres, I want to look at the space of pseudospheres. But I'm kind of missing something. Pseudosphere arrangements are missing something from vector configurations, and that is that they don't have the weights, and they don't have the R. And that's not important if you just want to find, for every oriented matroid, if you just want to find one realization, you don't care about the norm of a vector because it's not represented by an oriented matroid. But if you want to look at the global space, you do. So to look at the global space, the global topology, I add in weights. So I want to introduce a space of weighted pseudosphere arrangements where each of the weights is non-negative, and a weight goes to 0 if and only if the pseudosphere vanishes. And now I want to consider, so I have a space of weighted pseudosphere arrangements, and I want to consider now the space PSG, which consists of weighted pseudosphere arrangements on the k-1 sphere, but satisfying some conditions which are related to that of the Grassmannian. So if we recall, for the Grassmannian, n vectors that span r to the k. So I need something like spanning r to the k. And one way that you can tell a vector span r to the k is you can pick out a basis, and there will be no direction that's orthogonal to the basis that you picked out. The information that I have from pseudospheres is something like whether something is pointing toward a vector or away from a vector or orthogonal. So I should be able to pick out k elements from my pseudosphere arrangement that form a basis. And the way I test for that is there's no direction which is orthogonal to those k elements. And I test that by seeing that the zero sets of these k elements have no common intersection. And another part of the definition of the Grassmannian is that we quotient by the general linear group, but here, since we're working on the sphere, we just quotient by the orthogonal group. So now I have some space, but I want to add a topology. More than that, I would like to have a metric. So I add the Frichet metric, which is sometimes called dog leash distance. So this is defined by taking some parameterization between two pseudospheres. So for example, here I have a red one and a pink one. And I can think about this distance as being, suppose I had some person who was walking along this red one, and I had some dog he has a dog that's walking with him along this pink one. And the distance is what is the shortest possible leash we can use so that the person can walk along the red and the dog can walk along the pink, and the dog always stays within the distance of the leash from the person. So this would also correspond to how can you have a continuous map that sends the red to the pink, and take the minimum, the infimum over all possible maps from the red to the pink, and then take the supremum over the distance between each point and its image.
So are you allowed to go back?
No backtracking. Only one direction. Since it's in infinitum, you can like slow down and speed up, but you have to keep going around. So let's go back to these spaces. So now I have this space with a metric which sort of resembles the Grassmannian but is a little bit different. So the Folkman-Lorentz theorem, which says that every oriented matroid has a realization by pseudospheres, shows that this map OM tilde is onto. It's surjective. So the new thing that I show is that pre-images by this map are contractible. Yes?
That distance has something to do with the orientation, right?
Yeah. So the orientation is also relevant. So here, if this top part was positive for red and negative for pink, it would mean that the person has to walk this way and the dog has to walk the opposite way. But if they were both positive for red and pink and both negative for red and pink, then they are both walking the same direction. So there's some orientation. Another observation about this is, if I were to take this and just squish it together, this pink, squish it up into there, it would not converge. The pink would be diverging. If I wanted this pink to converge to the red, I would have to kind of push this part that's jutting back all the way in order to make a convergent.
So, just a comment.
Yeah?
Probabilists would call that the Skorod metric.
The what?
Skorod metric.
Skoron metric? Uh-huh.
Skorod? What
Okay.
is that?
Skorokhed.
Uh-huh. So I want to give some idea of how I show contractibility. So to show contractibility, I define some interpolation function which takes two weighted pseudo circle arrangements that have the same oriented matroid and gives as an output a homeomorphism of the sphere, and this should be some continuous function. And the main thing is that it sends my first, let's say this is my first pseudosphere arrangement and this is my second pseudosphere arrangement, it will give some homeomorphism of the sphere that sends the first one to the second one. So how can I do that? So for this I use some extension of the Riemann mapping theorem, which gives me, as long as I can determine 3 points on the boundary of a disk, this determines some unique conformal parameterization of the closed disk of that region by a closed disk. So I build up this interpolation function from one skeleton at a time. So I start with by mapping vertices to vertices. For vertices to vertices, I have no choice. If I pick out, here's where blue and green cross. There's two points where blue and green cross, but I could distinguish them by the sign of, say, black, whether black is positive or negative. So this point where blue and green cross has to be mapped to this point where blue and green cross. There's no other possible option. And so then if I go to edges and edges, I can pick out an edge, let's say this one. So for that, I choose some adjacent face to that edge, and I use my conformal parameterization of the disk, and I look at the unit speed on the boundary of the disk for each of those maps, and that gives me a conformal map to the disk, and then I interpolate using unit speed along arc length, and then I have a conformal map back. So that gives me a map from the one skeleton to the one skeleton, and now I want to go to faces. For faces, I just interpolate the map on the one skeleton to the inside using the conformal map. I just interpolate radially. So this gives me some, for two pseudo-sphere arrangements, two pseudo-circle arrangements, I have a map that sends the first pseudo-circle arrangement to the next, to the second. And now I want to use that to show that the pre-image of each oriented matroid is contractible. And for this, I use another tool. It was a theorem of Kneser that if you look at the space of self-homeomorphisms of the two-sphere, these strongly deformation retract to the orthogonal group. So how do I use this? Well, I want to choose some base point in the pre-image of some oriented matroid of the space of weighted pseudo circles representing an oriented matroid, and then do a deformation retraction from the entire pre-image to that base point. And the way I do that is for each x in the pre-image, I use the Kneser's deformation retraction to give me a way of mapping from the interpolation map back to something in the orthogonal group. And since I'm modding out by the orthogonal group, that becomes the identity. So for example, in the picture here, I have, say, this is the base point on the right. I pick something else in the realization space. I have my interpolation map, which sends my base point there. And then I use this deformation back to the orthogonal group to send that map back to the identity. So this will contract the pre-image of some oriented matroid to a point. So, and then the second thing I want to show is that the space of weighted pseudo-circle arrangements in the Grassmannian are homotopy equivalent. And to do this, I'm first going to assume that my arrangement is Z2 symmetric, because I don't want to go into details about that. And I will project to the projective plane, and then I will deform the zero sets of the pseudo-circles. So here's my starting pseudo-circle arrangement. So I want to deform this to the Grassmannian. And in order to deform this to this Grassmannian, I want to make all these curvy circles into great circles, which when I project, it means that I want to make circles and curves into straight lines. So to do this, I will use first a function that takes the mth for some sequence of the elements of the pseudo circles. For some sequence of the pseudo circles, I'll take the mth one in the sequence and make it linear in the faces of all the previous ones in the sequence. So first I project, and when I project, then I make here I make let's say black is 1 and blue is 2 and red is 3. Then I make the blue and the red straight lines, and I send black to infinity for my projection. And now I'm going to pick out one to be the fourth. I'm going to make this yellow one be the fourth one. So here I have a map that, so I just copied it now, and then I make the yellow one straight. And then the next one I'll do is the purple one, then I make the purple one straight. And then the green one, then I make the green one be straight in the subdivision of the plane by the cells formed by the previous ones so far. So at each point in this process, I haven't changed the underlying oriented matroid. I haven't changed the face structure, which means I can use the same deformation that I used to show that the preimage of an oriented matroid is contractible. So but now I need a second part to make these piecewise linear, these polygonal curves into straight lines. And for this, I have a second kind of deformation which makes the first M pseudo lines linear in the faces formed, makes the last, everything after M, linear in the faces of the first M minus 1. So here, first I'm going to make green be linear in the, so now green is linear in the subdivision formed by red, blue, purple, and yellow. So now I'm going to get rid of purple as part of that. So that means that now green will also be linear in the subdivision formed by just blue, red, and yellow. So here like that. And then next I'll make both purple and green linear in the subdivision formed by blue and red. And in this case, the oriented matroid changed. So sometimes in this process, the oriented matroid changes, and that has to happen sometimes because, so here was the change. The face structure is now different, which is what defines the oriented matroid. And sometimes that has to happen because they're unrealizable oriented matroids. And then finally, I make them all linear. So I have these two deformations, these two kinds of deformations. But even having these two kinds of deformations, if I have, there's something that I need here. In order to deform the first three to be straight lines, I have to have the first three form a basis. And also, some of these can go to 0 and disappear and reappear somewhere else. And that's going to be a problem. If the green one depends on the purple one, and the purple one disappeared and went somewhere else, then that's going to change the green one in a way that's not continuous. But all of this has to be continuous. So in order to deal with that, I actually define the deformation recursively by saying I first do the part F, which was in the beginning, and the part H was at the end. And then I can just use the magic power of recursion to say, in between there, the process works to deform things in the way that it should, so that I can do F first, and then the other elements in between, and then the remaining elements afterwards. So effectively, I have to go through every possible permutation. I have to recursively go through every possible permutation of the pseudo-circles to find a permutation that works, so that the first three are a basis, and that none disappear in the middle. So the last thing I want to do is go to how is this relevant to vector bundles, very briefly. And for this, I'll pick the third simplest vector bundle, which is the tangent bundle of the two-sphere. So if you want to find if you're living on the two-sphere and you want to find some coordinates for where you're living, here, maybe if you're in the equator, you can use east and north. But if you're around the North Pole, you need some other coordinates. You need 0 and 90. And maybe you would like to have a coordinate system that moves continuously around the sphere everywhere. And you always have two coordinates. But that's not going to be possible. Because if you could find such a pair of coordinates everywhere that changed continuously, that would mean that the tangent bundle of the sphere was a product space. But it's not a product. And in fact, you can't even find one vector field on the sphere that vanishes. So it's not going to be possible to use the same coordinates everywhere. You have to have multiple kinds of coordinates. But another way, rather than having different coordinates in different parts of the sphere, is you could pick 3 coordinates on the sphere. And a way that you could do that is by picking 3 height functions. So here, for example, I have a red height function going to the left. Here is this and a blue height function going up. And here, this will be the front of the sphere, and this can be the back of the sphere. And I have some yellow height function going into the page away from the sphere. So here it's coming out from this point and going into this point. And then if I have these 3 height functions, I can project to the tangent plane of the sphere. And then at each tangent plane, if I mod out by the general linear group, then I get a map from these 3 vector fields into from each point. These 3 vector fields define a map for each point on the sphere to some point in the Grassmannian. And then I can do another way I can look at this is I can pick out for each one of those, I have a corresponding oriented matroid. So I can subdivide the sphere by which oriented matroid appears in each part of the sphere, and I get something like this octahedron where I have these 8 different oriented matroids, and then they get mapped into the Macphersonian. So if you look at what this map is, so this the 2-3 Grassmannian is actually the projective plane, and this map becomes the 2-to-1 cover of the projective plane by the sphere, and the pullback of that map gives you the tangent bundle of the sphere. And the hope would be, the goal eventually is to use oriented matroids as a way of representing and working with vector bundles in this kind of way. So this is all I'll talk about.